Now the fifth point. Fifth point is very simple. It's on Bandt of equation. Bandt of equation. What is this? I'm sorry for this sorry for this bad handwriting. I hope you are able to hear and understand what I'm trying to explain. It says K1 equation constant at T1 Kelvin temperature. K2 is another equilibrium constant. It's not equation, it's equilibrium, okay? Equilibrium constant at T2 Kelvin. Okay, so there's a big formula here. It says log of K2 by K1. I'm not deriving it here. Okay, delta H naught upon 2.303 R, then 1 upon T1 minus 1 upon T2. Okay, this is the relation. Okay, now the sixth point. Sixth point is a some collection of formulas. It says delta G is delta H minus T delta S. You should remember this. Delta G is also equals to delta G naught plus 2.303 RT log Q. At equilibrium, delta G is always 0. So Q is equals to K equivalent, which implies that delta G naught will be equal to minus of 2.303 RT log K. Okay, let's do another. This is which number? Let me just check. 7th. Okay. Now here we are going to deal with formulas. It says AA, BP, CC plus TT. I hope you know what these are. What? These are number of moles of the corresponding concentration. Okay. So Kc is equals to, value of Kc will be what? Output products upon reactants. C raised to the power, concentration of C raised to power C, concentration of D raised to power D upon concentration of A raised to power A, concentration of B raised to the power B. Okay, next value will be of Kp. What will be Kp? To derive the value of Kp, you should remember that Pa is equal to Pt XA. What is this? Pb is equals to Pt X. It's mole fraction. Okay, XA and XB are mole fractions. Okay, Pc is equals to Pt Xc. Pd is equals to Pt Xt. So Kp, value of Kp, before you go on to Kp, you should remember these first. Okay, I'm considering all of them. Okay, then you'll say that Kp is equal to Pc raised to the power C. Again, it's products upon reactants. So it's since we are considering P pressure here, we'll be taking the ratio of pressures. Corresponding pressures, Pb to the power B. I hope you can see that I'm running very fastly because there are a lot of things that I need to teach you. So it's just a review. Kp is equals to Kc RT raised to the power delta Ng. Since this is also equal to, in terms of Kx, as Pt raised to the power delta Ng. Okay. Now we'll be looking at what happens when the equation is reversed, divided by something. Then we'll see the value of the new constant. Okay. Okay. When equation is, this is one block and another block says the value of the new constant. So first case, if the equation is reversed, I hope you are able to understand what does this means. AA is going as BB, so it is reversed, then BB is going as AA. So what's gonna happen in that case? So K dash, the new constant, will be reverse of the original one. Okay, second, divided by n. So k dash will be k raised to the power 1 by n. Third case, multiplied by n. Therefore k dash will be equal to k raised to the power n. Fourth, divided into two steps, and k dash will be equal to k1 of the first step, k2 of the second step. That will be the new constant. Okay. Next point to be noted here is a big thing. I've taught you this before also, but I'm writing it again. It is like, suppose you have some concentration at this level. Okay, you need to remember these values. The concentration is going to lie in between. This is the point, suppose, where R, reactance, is equals to products. So this is the case where equilibrium exists, that is Kc. Okay, and this is which position? Can you guess? This is reactants greater than products. And this is the case where reactants are less than products, because this is more, showing that products are more. Okay, that is why the value of the Kc will be according to it. When products are more, value of Kc will increase. Okay, so we have three cases here. What will happen if forward, backward, or this? We have Qc, three cases. Again, it's similar to that only, less than Kc, equal to Kc, greater than Kc. So what's gonna happen? Obviously this is gonna remain at equilibrium stage. This is going for forward reaction, this is going for backward reaction. Okay, forward reaction, backward reaction. Now let us note some important points. First, C of solid, CO2 gases, is going as 2CO gases. Okay, so we'll write initial moles as 1 going 0, next at initial condition 0. At equilibrium, when the reaction reach at equilibrium, moles will be how much? This is gonna be 1 by x. Why 1 by x? Because 1 minus x. Why? Because x is the number of moles which is transferred to that side, number of moles. Then this is going to be 2x, then it should be reduced by 1 by x. Okay, but remember, as I've told you, solid is not considered. This is solid here, this is not considered in the equation. So total moles, what will be the number of total moles? We need to calculate total moles. Total moles will be how much? This plus this, which is 1 plus x. I hope you've understood. Okay, next is your mole fraction. Let's understand mole fraction concept. And then you have, for mole fraction, what's gonna happen? This is again remaining 0 for solid. This is gonna be 1 minus x upon total. Obviously, what is mole fraction? Number of moles present divided by total number of moles at that stage. As you can see, we are not considering the solid. This is very important here. It's going to be 2x upon 1 plus x. Next, if you're asked to write partial pressure relation. Partial pressure, again, this is going to be nothing. This is going to be 1 minus x, 1 plus x into pressure, which is present at that time. 1 plus x into P again. Okay. What about the value of Kp? What will be the value of Kp here? Kp is very simple. Kp will be how much? Kp will be, again, this is 0, negative, it's not present anything, 2xp upon 1 plus x whole square divided by 1 minus x upon 1 plus x raised to the power p. Not raised to the power, sorry, multiplied by p, which is equals to Kp, which is equals to 4x square p upon 1 minus x square. You must be thinking, I have got the value of Kp. Kp is what? Kp is defined Kp is defined as uh, products upon reactants. This is the product here, partial pressure of product upon partial pressure of reactants. So you're getting this as a whole. Second point, it says if you have total pressure, okay, at equilibrium, if given, if you've been given with total pressure at equilibrium, and you are and sorry not and the Kp is asked, and you are asked to find out the value of Kp. So how are you going to calculate Kp? Let's take an example here. It says NH4HS solid is converted to NH3 gaseous plus H2S gases. So initial moles will be 1, nothing here, and at equilibrium moles will be how much? This will be X transferred to this side, and this will not be 1 minus X. Why 1 minus X? Not considered because it's again a solid here. Okay, so what is the total value? Total is the combination of these two, that is 2x. Nothing else is considered here. Okay, now mole fraction. Can you tell me the mole fraction? Okay, mole fraction will be x upon 2x, x upon 2x. What will be the value of partial pressure? It will be, partial pressure will be this whole thing, 1 by 2 into Pt. This is again 1 by 2 into Pt. Okay, and they are asking about P. What is Pt here? Pt is 6. If given in the question, supposedly if they give you the value of Pt, then you'll say that what is the value of Kp? Kp is this upon this, not this. From the previous thing, what we understood was Kp was equals to 4x square p upon 1 minus x square. So it should be it will be what? It will be Pt square divided by 4. Pt square divided by 4. Okay, and if you are asked to solve it by another method, supposedly you follow another method, there is method 2 also to this question. It says you have NH4HS as solid converted to NH3 gaseous, H2S gases. So what I'm going to do, I'll take this as a pressure P, and the total pressure, you should know that total pressure is Pt. So what will be the pressure of this? It will be Pt minus P. We will be neglecting this because it's a solid, it won't be considered. So Kp is equals to multiplication of both of them, products upon reactants. We don't have anything in reactants, so this is the value of Kp. Similarly, I've got this value also by multiplying these two quantities. Okay, I hope you are able to understand how we are getting these values. Okay, there is one more thing that I'll be telling you in this only. So now we have relationship between vapor density and degree of dissociation. Okay, so I'll take an example here. AA goes to as YB. Okay, if X is the number of moles which is dissociated, this is YX, 1 minus X. Initially it was 1 only. Okay, now total moles will be how much? Total moles will be addition of the two, 1 plus X into Y minus 1. If you'll add up both of them, you'll get this one. Okay, next is initial volume for 1 mole of A is V, suppose. Okay, initial volume for 1 mole of A is V. Okay, for 1 mole of A we have V volume. Then equilibrium volume for 1 plus X into Y minus 1, this whole quantity moles of A and B is how much? Can you guess that value? It's very simple. It will be just the multiplication of with the V. Okay. So now we have the relation as T is equals to density is mass per volume. It's the first equation. Then you have another density could be equal to mass. Whole total volume will be 1 plus x, 1 minus y minus 1 into V. Okay. So we have vapor density before dissociation. What is this? This is your vapor density before dissociation, and this is the vapor density after dissociation. Okay, so we will have the relation by dividing both of them. You'll get 1 plus x, y minus 1. That's the final relation, which is equal to iota, which is your what? Van 't Hoff factor I. Van 't Hoff factor I. And what is x here? X is your degree of dissociation. And what is y here? Y is your number of ions produced, as in the products. How many ions are produced in the reaction. Thanks for watching and stay tuned for my other videos. Subscribe to my channel, Ashutosh Academy.